three great papers in this session. And kicking things off is Amin. He's a first-year PhD student at Boston University, and he will talk to us about BOLTED, which is a new architecture for bare metal clouds.
Hello everyone. I'm going to present a new architecture which for bare metal clouds, which puts tenants in control of their own security. Today's clouds are great. They are affordable, they are reliable, and they are easy to use. However, they have massive trusted computing base, and they have huge attack surface. For example, OpenStack has millions of lines of code in their trusted computing base. Another problem we have is that the security model in today's cloud is trust me. Tenants need to trust provider for their own security. And we don't have any way to verify that the provider has implemented and deployed their services in a correct way, and these services are bug-free. Or even the provider has applied the latest security patches. Another problem is that we are sharing hardware between different tenants, and this creates the vulnerability for co-location-based attacks. We had Spectre and Meltdown attacks this year. Another problem is that the security level for all tenants are the same. They have to pay for the same security level which provider supports. Today's bare metal clouds, such as Amazon's AWS or IBM's SoftLayer, can solve virtualization problems. However, by not sharing machines between tenants, we will have no co-location attacks. However, bare metal clouds still have a large trusted computing base and attack surface. For example, OpenStack's Ironic has OpenStack in its trusted computing base. Another problem is that, again, we have trusted me model. Another problem is that the same fixed security for every tenant is here too. In addition, bare metal clouds introducing our new problems. The first problem is that we are exposing hardware vulnerabilities to tenants. And another problem is that provisioning a node in today's bare metal is slow. It may take several hours to provision a node. To solve these problems, we present BOLTED, which is a new architecture for bare metal cloud. It has following goals. It tries to minimize trust in the provider. It supports even the most security-sensitive tenants. Tenants can make their own trade-off between cost, performance, and security. And BOLTED supports provisioning time as fast as virtual. And BOLTED uses microservices, which most of them can be deployed by tenants, and they are not in trusted computing base. As a result, our attack surface will be much smaller. Let's see how BOLTED achieves these goals. Before that, we need to define some terminology. What is attestation? Attestation means checking hash measurements of softwares and firmwares running on a machine against the whitelist to be sure that the node is not compromised. Trusted Platform Module is a secure microcontroller which can store tenants' private data, including passwords and hash measurements. BOLTED architecture has three different services. First service is isolation service, which assigns nodes to tenants, networks to tenants, and connects them together. Using provisioning service, we provision a bare metal node, and using attestation service, we attest a node to be sure that the node is not compromised. And a bare metal node in BOLTED architecture can be in 4 different states. The first state is free pool. The node can be in rejected pool or tenant secure. It also can be in airlock. Using isolation service, we get a node and assign it to the tenant, and we put it in airlock. Airlock is an isolated state which the node is not connected to tenant's other nodes. In this way, we can be sure that the compromised node is not affecting tenant's other nodes. Using provisioning service, we download a secure firmware and client-side of attestation service on the node. Client-side of attestation service talks with attestation services server-side and attest the node. I am going to talk how we attest a node in the future slides. If attestation passes, we put the node in the tenant's secure pool and provision it. And if attestation fails, we reject the node. So how do we attest a node? First, we assume that each node of the provider has a TPM, and this TPM measures, stores hash measurements of the softwares and firmwares on the node. Using a secure firmware, we run a client-side of attestation service on the node. This client-side reads these stored values from TPM and sends them to the attestation services server-side. Server-side checks these measurements against the whitelist to be sure that the node is not compromised. BOLTED architecture gives a lot of flexibility to us. The only service we want from provider is the isolation service, which manages network switches and assigns nodes to the tenants. Other than this service, other services like provisioning service and attestation service can be implemented by developers, by providers or tenants. And this gives us a lot of flexibility. Here we have Alice, who doesn't care about security. She just wants to run her applications. So she gets provides isolation service and provisioning service and runs her application as fast as possible. We may have Bob, who is cautious more about his data than Alice. And he trusts provider. So he uses provider's attestation service, and in this way he can be sure that his nodes are not compromised by previous tenants. We may have also Charlie, who is very cautious about his data, and he wants nobody, including provider, have access to his data. He can use his manpower, expertise, and deploy his own provisioning services and attestation services. The only service he needs from provider is isolation service. For implementing BOLTED, we have used our own development. Hardware isolation layer is the only service we are having in our trusted computing base, and it only has 3,000 lines of code. And therefore, our trusted computing base is extremely small. We are using malleable metal as a service, or M2, as our provisioning service. It is designed to be stateless and uses network-mounted drives. Therefore, it is very fast. We are also using Keyline, which is developed by our team at Lincoln Lab as our attestation service. In this set of services, Hill, M2, and Keyline, is an implementation of BOLTED architecture. Another implementation of BOLTED can include other developed tools. For example, here, Charlie can use Ironic or M2 or adopts M2 to meet his requirement for his provisioning service. He also can use Keyline Plus, Keyline Prime, or whatever as his attestation service. This is another implementation of BOLTED. So I have talked about exposing hardware vulnerabilities in bare metal and today's bare metal cloud. What about this problem? Can we solve this problem? Today's legacy bias or stuck UEFIs are huge, and they are having a lot of problems. HEX is developed by our team at 2 Sigma, which is a stripped-down Linux firmware. It is a small and open source, so any developer can check for any bug in it. It also deterministic build, and it means that anybody can generate bit for bit identical kernel, unitary, and firmware images, and be sure that, and in this way, he can download the source code, build it, and check it to be sure that the running installed firmware on the machine is the same image he has built. We can use heads in BOLTED in two ways. We can download it to a stock UEFI and chain boot into it, or we can burn heads into the flash ROM. Actually, we have done it in our small set of our service. So I have talked about architecture and implementation. What about the security costs? What is the cost? Foreman is a standard provisioning service for bare metal. It installs operating system on locals, and in our environment, it takes more than 700 seconds to boot a node. Comparing to Foreman, we are using network-mounted drives, and therefore our boot time is very fast. It is near to virtual. As I said, attesting a node includes several steps. And if the tenant wants to have more security, his boot time will cost him time. In our environment, using stock UEFI and downloading heads, it takes 30% overhead comparing to unattested stock UEFI. Burned heads in flash ROM is a rare case that having security is even faster than unattested stock UEFI. And this happens because our post time is smaller than stock UEFI. And it is 10% faster than stock UEFI actually. We are evaluating BOLTED's scalability in a stress test. We are booting between 1 to 16 nodes in parallel, and our ceph pool is very small. In this environment, we have 50 seconds overhead against M2. In the real environment, this overhead should be less. Right now, Trammell Hudson from 2 Sigma is working with Open Compute project to integrate heads. We are working with Red Hat and open source community to upstream our technologies like including Hill, M2, and Keyline into Foreman, Ansible networking, and Fedora. And we're also working with DoD and medical services as our use cases. We would love to know more about use cases, so please let us know if you have any suggestions. And right now, the only firmware we are concerned is the firmware running on the processor. What about the other firmwares on the machine, including, for example, disk firmware or power supply firmware? To conclude, BOLTED minimizes trust in the provider. The only service we have in trusted computing base is isolation service. And hardware isolation layer, as our development, has only 3,000 lines of code. BOLTED supports even the most security sensitive tenants by letting them to implement and deploy their own services. Tenants can make their own cost, performance, and security trade-off. So if a tenant doesn't want to pay for security, he can use the cloud without security. And our provisioning time in BOLTED is fast as a virtual cloud. And BOLTED is using small services, and most of them can be implemented by tenants themselves. So our trusted computing base is extremely small. BOLTED actually it is not just in theory. We have implemented it, and it is working in our infrastructure in mass open cloud. Our source code is open, and you can see it. So if you want to check them, please talk to me. Thank you.